In the next video about thermodynamics in Chemistry 30, we're going to go through the concept of activation energy, the energetics of bond breaking and bond forming and catalysts as they relate to chemical potential energy diagrams. Our first theme is going to be activation energy. Before we move into activation energy, we're going to recap a little bit of collision activation theory and then roll into activation energy on the next slide. So the first point I want to recap about collision reaction theory is that all chemical species, regardless of their form, whether they're atoms, they're ions, they're molecules, they're in constant random motion. And the hotter the temperature of the system, the faster they'll be going and the bigger their distribution. Not all chemical species are going to have the same speed. A distribution of speed, but again, hotter equals an average faster speed. Now, when we do have a collision between two entities, there's going to be two possibilities. According to collision reaction theory. One is there could be a reaction. Some bonds are broken and some new bonds are formed. Second option is we just have an elastic collision. And this is what happens most of the time. There are nitrogen gas molecules and oxygen gas molecules bouncing off each other in this room, and they're just doing an elastic collision. There's no reaction. We're going to dive into why is there no reaction, because nitrogen gas plus oxygen gas can cause a reaction. Before I look at the two requirements for a reaction, let's take a look at a organic chem reaction, an addition reaction between hydrogen gas and propene. Now, in order for that green diatomic hydrogen to cause a reaction, it must get to that double bond. Our hydrogen molecule must hit our propene at the right point. If it hits it at the end far from the double bond, you're not going to get a reaction. Now, when we refer to this as the correct orientation, we have to have the hydrogen hit the double bond at the right part of the molecule, and often the correct angles are required. So if they don't hit each other in the right spot, no reaction. Hit each other at the right angles, no reaction. And even though you may get collisions between molecules that have the right orientation, they have to hit each other with enough energy to cause an initial bond breaking. There is a minimum energy required for that, for any reaction, and we're going to call this activation energy, and we'll dive into it more in the next slide. So I'm putting a little subscript A, to give a note to this type of energy. So let's dive a little bit more into activation energy. In particular, you need to be able to identify and quantize the activation energy on a chemical potential energy diagram. So what is activation energy? As previously mentioned, that's the energy required to get the bond breaking going, to start the reaction. Even in exothermic reactions, combustion reactions, you still have an activation energy. Wood and oxygen will not spontaneously combust in all circumstances. There has to be enough energy to get that reaction started. An example of providing activation energy would be when you light a match to start a fire. The heat coming off that match is enough, provides enough energy to get the reaction started. So let's take a look at a chemical potential energy diagram for the combustion of methane. Now, this wording should be enough for you to write a balanced chemical equation, so I will start there. So methane, meth is 1 carbon, CH4, and the 1, 2, and 3 carbon long chains are all gases. Combustion will be plus oxygen gas. This will make carbon dioxide gas and water vapor in complete combustion that is open. And this reaction requires 1 methane, 2 oxygen, and will produce 1 carbon dioxide and 2 units of water vapor. So let's present this reaction on a chemical potential energy diagram. The axis are going to be reaction coordinate, which I tend to shorten as RC, and we're going to have potential energy on our y-axis. We're going to have our reactants at some initial potential energy. Now, I haven't calculated the change in enthalpy for this reaction, but I know it's combustion, so this must be an exothermic reaction with a negative enthalpy change, so my products must be lower than the reactants. Okay. And on a chemical potential energy diagram, the first thing we see upon moving past the reactants is an increase in potential energy. That is the putting the energy in needed to start this reaction. Okay. And at some point, you will reach the maximum potential energy. Okay. This top point is often where it's said that there's an activated complex. This is in the middle of the reaction where there's a bond, maximum bond breaking occurring, atoms being separated from each other or breaking those chemical bonds. Okay. After the bonds have been broken, new bonds are going to be formed until you get to the enthalpy, the potential energy of the products. Okay. So that upward path, which I color-coded blue, is our activation energy, and we often show this with an arrow. Okay. You must have the blue pathway in the diagram. The green arrow is showing the energy of activation. The energy is always up. You always must put energy in. You will never see an activation energy arrow pointing down. Okay. Now, just for recap and emphasis, the enthalpy change, which has been talked about a lot in this unit, is just the difference between the beginning and the end. So that red arrow represents our change in enthalpy, or our change in potential energy between the beginning and the end. Putting a dotted line in to highlight that arrow starts exactly at the enthalpy of the reactant and finishes at the enthalpy or potential energy of the products. So that wraps up our conversation about activation energy. Next, I want to move into the notion of bond breaking and bond forming, and we're going to come back to a very similar diagram to the one we're just leaving. First, we're going to talk about the energetics of what happens when you break a bond and what happens when you make a new bond. Before I do that, we'll just get thinking about this topic of bond energy, okay? Which bond energy is the energy required to break a bond, okay? To pull them apart. Okay? An example would be if you had sodium chloride, okay? This is the energy to get the sodium and the chloride pulled apart from each other. Okay? And this is a breaking of a bond, and that's the first part of a reaction we want to talk about. Okay? In all chemical reactions, we're going to have some bonded particles and it's always going to require energy to get them to be separated. Okay, this is exactly the bond energy from the first line. Okay. I'm going to call that A, and we're going to relate this to a chemical potential energy diagram in a second. Okay. My analogy to help remember that you always need energy to separate bonded particles is to think of magnets. Okay, if you have two magnets stuck together, bonded together, you always have to put energy in to separate them apart. Okay? Taking original particles or molecules and separating them is a endothermic process. Okay, it's always an energy requiring process. Okay. That part makes a lot of logic, is very logical, particularly thinking the magnet analogy. What's a little harder to realize, but is always true, when you have separated particles or separated atoms and they form new bonds, you always get a release of energy. So it will always be a product term, and this is going to be our exothermic part, or our releasing of energy part of our chemical potential energy diagram. Okay, so now I want to relate when do we see bonded particles coming apart, and I'm going to color code that red, and when do we see separated particles releasing, coming together and releasing energy, and I'll color code that blue. Okay. And we're going to take a look at the decomposition of water for this example. So I'm going to get started with my chemical potential energy diagram and then label the red A part and the blue B part. Okay. First, I like to get my axis in, so reaction coordinate on the x-axis, potential energy. On the y-axis, we're going to put some numerical values in, and we're going to do those in kilojoules. Okay. We are starting with 2 water molecules in this decomposition. Okay. So I'm not sure exactly what enthalpy. I'm starting in the middle of my chemical potential energy diagram. So 2 water, and that's it. We are ending up higher because our enthalpy change is positive. There's an increase in enthalpy for our products. 2H2 gas plus O2 gas. Okay, and I'll draw in that enthalpy change right away, starting at reactants up to products, and that is 571.6 kilojoules up. Okay. Okay. So now let's add in the bond breaking and bond forming, connecting the beginning and end, or reactants and products. So first, we're going to have bond breaking. We've got to take the bonds in water and break them up. Okay. If we think of our water molecule, and then we look at our products, okay, there are no OH bonds in our products, so both of those bonds must be broken, and that is going to require energy. That's going to be our part A. Okay. So we're going to need some activation energy to do this, and that is the going up. As we're putting energy in to break those bonds, we're going to see an increase in potential energy. Okay. Once we get those O's and H's separated from each other, they're going to start coming together. Okay. The process is going to start at the activated complex at the top, and the energy released as those new bonds are formed is going to be our drop. Okay. Now the red up and the blue down are never going to equal each other. One of them is going to be larger. Okay. In this particular example, okay, the red, which is the endo piece, okay, is larger. Okay. Than our blue, which is the down, which is the exo piece. Okay. Because the red is larger, okay, overall we're going to have an endothermic reaction in this case. The red, the endothermic piece is bigger. Okay? If we had an exothermic reaction, the red up would be smaller, the blue down would be bigger and would have an overall release of energy. Okay? But all reactions are going to have these two pieces. Before we move on and wrap up catalysts, we're going to think of reactions a little bit differently. In one of our following units, we're going to look at equilibrium reactions that go both ways. Okay? And for reactions that go in both directions, we don't have to redraw these chemical potential energy diagrams to think through this process. Okay? We can think of what would happen and what would our values be if this reaction went the other way. What if we started with hydrogen and oxygen and went and made water in reverse? Okay. Well, that would be starting with our products and going backwards. Okay. So what would the change in enthalpy be for the reverse? Well, that would be starting again at our products, going back to the reactants. Okay? It would be exactly the red arrow, but in the opposite direction. Okay? So the reverse reaction, the enthalpy would just have the same number, but it would have the opposite sign. So enthalpy change forward, enthalpy change of the reverse, same number, flip the sign. Okay? Now if we think of the activation energy, it's not as straightforward. Okay? I'm going to put in the activation energy forward in green. So this is our barrier. The energy we have to put in to break everything up in the forward direction. If we think of the reverse direction, starting at our hydrogen and oxygen, the barrier ends up becoming that smaller blue hump. This is the activation energy for the reverse reaction. Okay. And these are likely testable skills. What would the enthalpy change be for the reverse reaction? Just flip the sign. What would the activation energy be? You'd have to interpret the graph. Okay. You would have to have a labeled axis and be able to read the values off your y-axis. Okay. So that's our second concept, bond breaking, bond forming, relating them to a chemical potential energy diagram, and going a little deeper and thinking of forward and reverse. Okay. Last concept is catalysts. Okay. We're going to talk about this largely just from a graphical perspective. Okay. So I'm going to do a generic chemical potential energy diagram for an exothermic reaction. So we're going to start with our reactants at some enthalpy. We're going to finish with our products at some lower enthalpy, okay, because this is an exothermic reaction. Okay. And if we have just what we've had so far, no catalysts, we're going to have this blue connection. We're going to have our activation energy, activate a complex, and drop down and release energy to our products. Okay. And everything blue is going to be no catalyst. We have our activation energy. We have our change in enthalpy. Okay. Okay. Then we're going to look at what happens if a catalyst was used. Okay. Now there's a lot of types of catalysts, and we're not going to dive into that. Some are metallic metals can work as catalysts, such as platinum. There's lots of biological catalysts in our bodies that will allow reactions to occur. Okay? So we don't care what type, we don't care how it happens, but we see consistent trends. Whenever you add a catalyst, you always lower the barrier. Okay? That is what a catalyst does. If it doesn't lower the barrier, it's not a catalyst. If it raises the barrier, it's an inhibitor. It's not a catalyst. So we're going to see a lower top. So we have to start at the reactants because the catalyst is not going to change what reactants we have. It's going to have a smaller barrier. And then even though we have a catalyst, we're still going to get to the exact same products. We finish at the exact same place. So if in red I label those key characteristics we've been talking about chemical potential energy diagrams, our activation energy from reactants to the top is going to be a smaller arrow. Our enthalpy change is identical. That is still from reactants to products. There is no change in enthalpy change. Now to help convey that, I'm just going to put a dotted line in to show that the start of both the blue and the red arrow is exactly the same enthalpy or potential energy of the reactants. Okay. So I've summarized a few key things you have to know that have been said orally in the bullets down below. So the first one you have is that catalysts lower the activation energy for a given reaction. Okay, that's the blue upwards arrow by the reactants compared to the red. Second bullet. The fact you added a catalyst does not change the delta H. Okay? The change in enthalpy is exactly the same before and after. Okay? So if I ask you what's the enthalpy change before and after, and I give you the value of 1 of the original, if it's minus 100 kilojoules with a catalyst, it'll be minus 100 kilojoules without 1. Okay? What a catalyst does is lower the activation energy, and that increases the rate of reaction. If you have a smaller barrier, way more molecules are going to get over that barrier. Okay. Now we don't study rates of reaction, but that's the big change of a catalyst. It doesn't change a lot of our enthalpy calculations. Okay. Catalysts create an alternate pathway for every reaction that you add a catalyst for. Okay. So that concludes the 3 characteristics we needed to study of chemical potential energy diagrams.